So in this lesson, we're going to learn how to transform power functions. Now, last year in grade 11, you spent quite a bit of time transforming all sorts of different functions. So I won't go over all the small details about transformations like we did last year in grade 11, but I will show a short animation to help refresh your memory of transformations because you probably haven't touched transformations in quite a while. So in this lesson, we're going to be transforming power functions. Now, I won't go into as much detail as what you may have done in grade 11 when you're transforming the quadratic function, the linear function, the square root function, reciprocal function, and maybe even the absolute value function. You learn how to generate the mapping rule and you learn how to say transformations. But we're going to quickly go over the same ideas. In this unit, we're transforming power functions. So it could be a quartic, could be a cubic, quintic, whatever. And you have your four parameters. You have A, K, D, C. I'm hoping you remember what A, K, D, and C each do. But if you forget, then hopefully the animation reminds you. So I'm going to change A. So hopefully take a look at it. I'll let the animation keep running. Okay. And of course, this red dash graph is our base function. Okay, let's return that back to 1. What about k? Beautiful. Okay. And d? Perfect. And last one, c. Okay. So hopefully, let's start with the easiest ones. We'll do D and C. So D is going to tell us what the horizontal translation is and what the vertical translation is. So, I don't know, let's say D is 2 and C is, I don't know, -3. So that means you went 2 units to the right and 3 units to the left. And I want to add the fact that you can determine where the new location of the point symmetry will take place. The point symmetry of this transform function will now take place at 2, -3, because the point on the origin, or where the point symmetry used to exist, is now located at 2, -3. So you need to know where that new point is, because that point is critical in terms of helping you graph the transform function. Same, like for example, if I were to graph a parabola, the most important point you can argue for is the vertex. If you know where the vertex is, the rest of the graph is much easier to work with or to create. Okay, so let's go back to a 0 here. Okay, so if A is equal to 2, you have a vertical stretch by a factor of 2. And if A was 0.5 or 1/2, now the textbook will say it's a vertical compression by a factor of half, but I strongly disagree with that because if you think about it, it just doesn't make any sense when you say vertical compression by a factor of half. So I would argue that it's a vertical compression by a factor of 2. I'll spend more time explaining why it's vertical compression by a factor of 2, but we'll save that for the transformation lessons for grade 10 and grade 11. And if it was negative, then there's a reflection with respect to the x-axis. K, let's say K is 2. If K is 2, you horizontally compress it by a factor of 2, and that's also different from the textbook because the textbook says horizontal compression by a factor of half. If K was equal to half, then we can all agree that it's a horizontal stretch by a factor of 2. And if it was negative, let's say negative 1, then it's a reflection with respect to the y-axis. Okay, so that's all the things you did last year. I'm just going to change it to a quartic just to show you could be transforming cubics, quartics, quintics, doesn't matter, any power function. So that's what we're going to be doing in today's lesson, just transforming any power function you want.
Okay, so hopefully that animation was pretty helpful and refreshed your memory. So if you want to graph transform polynomial function, or transform power function specifically, the strategy is exactly the same as last year. You find the key point of your original function, your parent function or your base function, and then you find the coordinates of the transform key points by using your mapping rule, and then plot, 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 and connect the dots, and you have your new transform function. Last year, you also talked about the order in which you apply the transformations. So you have to apply stretches, compressions, reflections, and translations. You can actually switch up the order as long as translations end up being the last. Okay, and then the mapping rule, it's 1 over kx plus d, ay plus c, which is basically what we said earlier when you state transformations. You state the stretches and reflections first, and then you tack on the translations at the very end. All right, so what we're going to do is graph g of x, which is a transformed cubic function. So let's see, a is equal to -3, k is equal to 2, d is -1, and c is equal to 5. So I actually gave you the original points, and I asked a quick question. I said, why did we choose the integers from -2 to 2 for our original points? Because you could have chosen, let's say 5 to 10. Okay, you can choose the x values from 5 to 10, but that would be a pretty bad idea. So you choose -2 to 2 because hopefully you remember how your power functions look like. So your power functions basically look like this or this. Okay, there's the linear one, but we're going to ignore the line. Okay, so they basically look like some variation of the cubic or some variation of the parabola. And if you remember this to be the graph, then it makes sense why we chose the x values to range from -2 to 2, because that will give you the center of the graph. You want the new positions of these points in the middle of the graph. So when you do transform it, you still have the main picture. How should I say it? Like if you transform it, you don't really want to see that. You don't want to see a little piece dangling off to the side. You want to see, the vertex of the parabola, for example. You want to see where the point symmetry exists. Okay, so why do we choose? We want the center of and I use it very loosely, center of the graph. Okay, you want where the exciting thing happen? That's what we want to see. Okay, all right. So now what we're going to do is find new points. So I'm going to write down the mapping rule. So xy becomes, let's see, 1/2 x minus 1 and -3y plus 5. So when I see 1/2 x minus 1, I see a horizontal compression by a factor of 2 and a horizontal translation 1 unit to the left. And here I see a vertical translation by vertical stretch by a factor of 3, and a vertical reflection with respect to the x-axis, and a vertical translation 5 units up. The key thing I want to say is this, the 1/2 here. Okay, you're taking your x values and halving them. Okay, so it makes sense to say a horizontal compression by a factor of 2, because the textbook would say horizontal compression by a factor of half, which just doesn't make sense, because if you want to have something, the language of horizontal compression by a factor of 2 would be better than horizontal compression by a factor of half. But anyways, as long as you solve for the points correctly, then that's really the key thing here. And generating the correct mapping rule. Okay, so let's see. -2, so -1. -1 subtract by 1 is -2. And so -1, so let's see. -half, -1.5, -1, -1/2, and oops, that's 0. Let's check. 2 times -2 is negative something, something to check out. Let's check. And then 1/2, and 1/2 times half minus 1 is -half. 2. Oh yeah, okay, perfect. 2 times half is 1. 1 minus 1. Okay, good. Let me clean that up. Okay, so now, based on the fact that this was a cubic, I can see some symmetry. So 24 plus 5 is 29. Okay, -3 times -1 is 3. 3 plus 5 is 8. 0, 5. Okay, so remember, point symmetry still exists even though you transform it. So, using logic, you should be able to generate this number. Now, if you can't see it, then you have to just plug it into the expression 3y plus 5 and evaluate. So -3 plus 5, 2. And it makes sense. You want to have this to be 2 because you want to generate point symmetry. -24 plus 5, -19. And once again, this should generate some point symmetry here. Let's see, 8. And yep, 2 to 9. Yep, perfect. See, a difference of 21 and difference of 21. All right. So, and you know what? Later on, we're going to plot the points, and you'll see that there is point symmetry that exists. When you plot the point symmetry doesn't show up, then you know you did something wrong. Anyways, these are the key points for your transform function. Plot, 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 and connect the dots. So we're going to practice the plotting, so that's why I didn't give you space for that example. All right, so the things to do here. Describe the transformations, write the corresponding equation, and graph the function. So you know what? I'm going to start off by writing the equation and state the domain and range, sorry. Okay, so vertical stretch by a factor of 2 horizontal stretch by a factor of 3 horizontal translation 5 units right. Now some students, they have trouble stating transformations, so what I would suggest to them is write down the parameters first. So you write a equals 2, k equals 1/3, d equals 5, and c equals 0. So write down the parameters and then state the transformations if you're having trouble. Because what I'm doing is I'm writing down in my head and then I'm stating transformations. Okay, so I did the transformations, I wrote the equation, and I need to graph the transform function. But in order to graph the transform function, I need to find the points. So the original points, okay, so these points are for f of x, these ones are for g of x. Okay, so the original points, remember, -2 to 2, because you want the center of the graph. So this is a quartic. All right, quartic, and there's line symmetry with the y-axis and the mapping rule. We need that. So I'm going to write it up here. I'm going to try to sneak it in there. So horizontal stretch by a factor of 3. So triple the x coordinates and add by 5. And then multiply y coordinates by 2. Because you're vertically stretching by a factor of 2. So when you state the transformations, you should really relate it to the mapping rule. Okay, there's really, they match up with each other. Each sentence or each little point you make, it corresponds to the correct operation you're applying to the coordinates. Okay, so I always read it and write down the mapping rule and connect the two. All right, so -2, -6 plus 5 is -1. And then you just add by 3. I'll just double check. This is 2. Good. Add by 3, add by 3, add by 3. Beautiful. And now it doubles. This is 32. Not very good. That's going to be a little tricky to plot, but we'll manage. Okay. Let's grab a ruler here. So all the points here are positive, so I don't need to use much of quadrant 2, 3, or 4. So let's do 1 here. So every teacher asks for different things when it comes to scaling, but I'm just happy with just seeing one number and I can piece together the rest of the scale. I don't need you to give me all the numbers. Can I fit 32? Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Yes, perfect. Okay, let me just cheat a little. Okay. So, -1, 32. Beautiful. 2, 2. 5, 0. And then based on the symmetry, that must be the case. Okay. Beautiful. And do I see line symmetry about the ooh, that was not good. Let's try that again. Do I see line symmetry about the line of x equals 5? And the answer is yes. So, feeling pretty good. Oh, I'm having a hard time doing this one. Alright, let's give it more space. Let's start from here. Beautiful. Okay. Beautiful. So they want me to state the domain of the transform function. I wasn't very clear, but I definitely want the domain of g of x. I don't really care about the domain of f of x, because I expect you to know how to state domain and range of power functions. That's pretty straightforward. Domain, easy peasy, always all real numbers. Range, greater than or equal to 0. And that global minimum point used to be at the origin, but now it's 5, 0, which makes sense because your translations are 5 to the right, and there is no vertical translation. So it used to be 0, 0, now it's 5, 0. So it makes perfect sense. Everything is checking out so far for this graph. Okay, first thing to do is factor out that -2. Remember, if it's not factored out, you will probably state the incorrect horizontal translation. So factor out -2. And now I'm just going to write the equation. We're transforming quintic. Ooh, okay. So now let's state the transformations. Vertical compression by a factor of 4. So the textbook will say vertical compression by a factor of 1/4. But like I said, you're taking the y coordinates and multiplying it by 4, or you can say, multiplying by 1/4, or you can say dividing the y coordinates by 4. If that is what you're doing, if you're dividing the y coordinates by 4, the language of vertical compression by a factor of 4 makes much more sense than vertical compression by a factor of 1/4. Okay, horizontal compression by a factor of 2. Reflection with respect to y-axis. What else? Horizontal translation. Three units right. And vertical translation. Four units up. Okay, so now we're going to state the mapping rule. We won't forget this time. So, horizontal compression by a factor of half, reflect it with respect to the y-axis, and go 3 right. Vertical compression by a factor of 4 and 4 up. Okay, these are the original points, and these are the transform points. So -2 to 2 to get the center of the graph. And then we are going to find the new points. So let's see. 1/2, -1/2 is positive 1, 1 plus 3 is 4. And then drop it by a half. So 3.5, 3, 2.5, 2. And then a quarter, so that's -8 plus 4 is -8 plus 4 is -4. Let me triple check that. -8 plus 4, correct. And then -1/4 plus 4, so that's 3.75. 4. You can figure out the other values using symmetry. 4.25, and that should be 12. Okay, so, and by the way, because it's a quintic I'm transforming, I know the domain. Domain and range is all real numbers. And I don't really want to get you confused with f and g. This is domain and range of g. I'm going to do that for the first example too. G. So it's not f. Okay, so I just need a scale and then I'm done. So this one, you know, I'm going to go more in the middle. Actually, no. Over here. Okay, and then I'm going to do over here. So we'll do 1 and 1. So 1, 2, 3, 4. 1, 2, 3, 4. It's funny because I was teaching my two kids, they're JK and SK, and I was teaching them how to plot points. I should get them to do this. 3.5 and 3.75. Okay, and then 3, 4. 1, 2, 3, 4, and 2.5, 4.25. Ooh, did I give us enough room? Let's see. 2, 4, 6, 8, 10. Oh no, I forgot to give myself enough room there. Let's check. Did I count right? 2, 4, 6, 8, 10, 11. You know what? I'm not doing that over. That was a bad mistake on my behalf. So, you know what? Let's change the scale. That was I should have lowered the x-axis. I wasn't thinking. So I'm going to change the scale. Sorry about that. Let's do one more time. So 1, 2, 3, 4, -4. And then 3.5, 3.75. So this is 4, so it's somewhere here. Then 3, 4, then 3, 2.5, 4.25, and then 2, 12. 2, 4, 6, 8, 10, 12. Beautiful. Point symmetry, I see it. Boom. Okay. All right, let's do the next example. Okay, let's start off by factoring first. Main equation is a cubic we're transforming. Okay, so state the trend vertical compression by a factor of 2, horizontal compression by a factor of a third. Oh, whoops. By a factor of 3. I was thinking what the textbook wrote. Yeah, because it makes sense because I'm going to multiply the x coordinates by 1/3 when you look at the mapping rule. Horizontal compression. Oh my goodness. Translation. 2 units right. Vertical translation 1 unit up. Let's do the mapping rule. So 1/3 because you're compressing horizontally by a factor of 3. No reflection, 2 units to the right. Vertical stretch by a factor of vertical compression. So what that means, it's going to be half of the previous y values, and I'm going to increase by 1 unit up. Okay, so, and you know what? I can tell you the domain and range is going to be all real numbers because this is a transformed cubic. So, the points for f of x and the points for g of x. So this cubic, so -8, -1, 0, 1, 8. Alright, so let's see. One that's -2/3. -2/3 plus 2 would be 4/3. Let's double check. -2/3 plus, yep, 4/3. And then you're just going up by a third. So it's going to be 5/3 and 2, and then 7/3 and then 8/3. Okay, and then you're having the y, so -4. -4 plus 1 is -3. -half plus 1 is half. And then 1, and then 1.5. 8, 4, 5. Perfect. Let me check the values, make sure there is point symmetry there. Yep, there's point symmetry. Okay, point symmetry about the 0.21. Okay, this time we're not going to make a silly mistake here. Alright. These numbers are smaller, so like 5 and -3. Okay, so this one I'm going to do 1/3 as my scaling, and I'm going to do 1 for my vertical axis. Okay, so 2, 1. So let's do 1/3, 2/3, 1, 4/3, -1, 2, 3. And then 5/3, half. And 2 is 1. And then 7/3 is 1.5. And then 8/3 is 5. 2, 3, 4, 5. Beautiful. Something looks weird here. 2, 3, 4, 5. Oh, it's because this point. 1/2. It's not -1/2, it's +1/2. Alright. So I knew there was a mistake. It just, like, point symmetry didn't exist there. But now that I fixed the point, much prettier. I see the point symmetry. So always look at the points and see if the symmetry exists. And if the symmetry does exist, you're most likely to be correct. Okay. Let's keep going. Last one. Transforming a quartic here. Ooh, I see a bunch of transformations. Or a bunch of reflections. And I think it's rather silly. I'll tell you why. That's a 2 there, sorry. So it's silly because if it's a quartic, why am I reflecting quartic with respect to the y-axis? It's already symmetrical about the y-axis, so really that transformation does nothing. It won't change anything. So I'm tempted to not even put that negative there. But you know what? I'll just leave it. Okay. So you know what? I'm going to show you something interesting. To obtain g of x, you could state that you could say reflection with respect to x-axis, reflection with respect to the y-axis, horizontal stretch by a factor of 2. You can say horizontal translation 2 units to the left, and a vertical translation 2 units down. But what I'm going to do, I'm going to use algebra and simplify, because that was 1, 2, 3, 4, 5 transformations. I can make it a little easier. There's another way I can transform f of x to get g of x. So what I'm going to do is just simplify this algebraically. This is a 1 over 16. So instead of doing 5 transformations, I'm just going to do 4. Because 1 for the reflection, 1 for the vertical stretch, and then a translation, a horizontal and a vertical translation. Okay. So let's write it down now. Vertical stretch, compression, whoops. I actually teach my students that they can also say vertical stretch by a factor of 1 over 16, but I'll be consistent with the rest of my lesson here. Vertical compression by a factor of 16, because a vertical stretch by a factor of 1 over 16 is multiplying by 1 over 16, which is the same as dividing by 16. Anyways, vertical compression by a factor of 16. So the last comment I'm going to add is that a vertical compression by a factor of 16 to a quartic is equivalent to a horizontal stretch by a factor of 2, because if you did 2x to the 4 and 1 over 16 x to the 4, so this is a vertical compression by a factor of 16. This is a horizontal, sorry, let's say 1/2. This is a horizontal stretch by a factor of 2. If you were to expand this or simplify this, you'll get 1 over 16 x to the power 4, which is the same thing as before. So that's why you can actually create an equivalent horizontal stretch factor or horizontal compression factor to offset that vertical stretch or compression factor. Now, you got to be careful because the numbers change when it's a different base. So if it's a quintic, then the numbers change because it's a power of 5 as opposed to a power of 4. Anyways, all I'm trying to say, there are different combinations of transformations that will bring you to one function to another function. You could apply what seems to be different transformations, but your end goal will be the same. Okay, let's finish the deal here. Reflection with respect to x-axis, horizontal translation, 2 units left, vertical translation, 2 units down. Okay, mapping rule. So let's see, x minus 2. and then 1 over 16, negative 1 over 16, y minus 2 of x, center of the graph, and then g of x. Oops, I forgot the y values. It's 4, so it's 16, 1, 1, 16. And this is now, let's see, subtract by 2. So negative 4, negative 3, 0, oops, negative 2, negative 1, and 0. There we go. There's my 0. Now, 1 over 16, negative, let's see, this one's easy. And then negative 1 minus 2 is negative 3. Negative 1, and then 1, so negative 2 and 1/16. That's what's 1/16. Negative 2.0625. We're going to have a blast plotting that. And negative 3. Let's just check everything out. Okay. Okay, here we go. So we'll do 1 here and 1 here. So negative 4, 1, 2, 3, 4, 1, 2, 3. And then 0, negative 3. Boom. Beautiful symmetry, I see. Beautiful. Beautiful. Domain of G, all real numbers, of course. And the range of G is anything less than or equal to negative 2. Okay, so we're finished with the transformation lesson. Very, very similar to what you did last year. So really go for what you did last year with transformations, and this lesson should be pretty straightforward.